So far, we've only talked about temporal locality. So let's now talk about spatial locality. Spatial locality is when we pull in more than just the word that we're accessing. So in the prior examples, we were pulling in just one word at a time to the cache. But now, even though we're accessing still a single word, we're going to pull in multiple words for every memory access. So we're going to increase the block size. In our prior examples, the block size was just one word. Now we're going to make it have a block size of 4 words. Okay, our capacity is still 8 words, and so now we can only have 2 sets. So set 0 and set 1 here. And so we're only going to have a single set bit. Log base 2 of 2 is just 1. But now we have this new field in our memory address called a block offset. And because our block size is 4, we're going to have 2 bits in that block offset. Had our block size been larger, like 8 words, would have log base 2 of 8 is 3 bits, or 16 words, then we would have had 4 bits in the block offset. But we have 2 bits here because our block size is 4 words. And so that will tell us which word within the block do we actually want to access. Okay, so after we read the data, we're going to choose which word within that block we want. So it looks almost like an associative cache, but it's not. This is a single block, but the block is 4 words wide instead of just 1 word. But it's still just a single way, right? For a direct map cache, we just have one way in that set. And so the number of blocks that we can store is just the capacity over the block size. 8 over 4 is 2, so we just have 2 blocks. Here's, one block top here, and then we have our second block there. And so we're going to use that block offset to tell us which word we want. So let's suppose we have some address here, just kind of slowly making it up. Let's suppose we had that one, and we'll go ahead and do ones here. Let's just do them in order here. So word 0, word at address 0, word at address 4, word at address 8, oops, word at address 8, go, and the word at address 12 or C. Okay, so still we ignore our byte offset. This would tell us which byte within the word we want. We're not going to worry about load bytes. And so this is still our byte offset. Ignore those. The next bits are our block offset. So we use 2 of those bits. That tells us which word within the block that we want. And in this case, we only have a single set bit. So this next one tells us which set it's going to be in. So these addresses, again, address hex 0, hex 1, hex 4, hex 8, and hex C, these all map to the same set. You can see they all map to set 0, but the block offset's different. So no matter which one of those I access, I'm going to pull in that entire block. So address 0, 4, 8, and see, I'm not drawing the data, I'm just drawing the memory addresses. The data, each of these addresses would get pulled in. And then I would use the rest of the bits D. So then the remaining bits would be the tag. Right? Our tag bits are everything else. Our tag bits, and that tag is the same, you'll notice, for all those, all 0 in this case, and we'd make that valid. So let's say I did an access to address 8, hex 8. So I did something like this. I did a load word, T0, making up an address there, hex 8, 0. If I access that word, so or this word at address 0, I'd pull in not only the word at address 8, but it also pull in the words at addresses 0, 4, and C. So it pulled in that entire block. And now to tell which one I actually want, I'm going to use this block offset. It's here to tell me which word I want. For address 8, we go and say, okay, I want this, this word 10. That's the one I actually want. If later I didn't access to, right, so after this, if I didn't access to, instead of word 8, we change it and we say, well, now the next access comes to, let's say hex C. Already in the cache, and now instead of accessing word 8 here, I would look at the block offset. Hex C is this address here. Block offset, again, are these 2 bits here. Would look at that block offset and would say, okay, I want address hex C within that block. Okay, but the nice thing is that first access to address 4 pulled in that entire block, and so when the next access came to that block, hex C, didn't have to pull it from memory. It was already there because of spatial locality. So here's another example, some other address here, hex 80000009C. And so this one, again, we ignore the byte offset and we look at the set. So this maps to set 1. And in this case, the word that we actually want is up here, right? The block offset is 11. That tells me which word I actually want, hex 9C, but also pulls in hex 8, all zeros, 9, 8 here, 9, 4, and 9, 0. So if another access came in, maybe after this load word came into hex all 8, all zeros, 9, 0 instead, the block offset would say 0, 0 here and would pull that data that I hadn't even accessed before, but because of spatial locality, it's there, and we'll pull out that data from our cache. So here's an example showing the advantage of spatial locality. So let's look at these addresses. These are hex 4, 12, and C. We actually looked at those. I mean, excuse me, not hex 12, but 4, 8, and I said hex C, but it's written as 12, same thing. And so remember that these addresses are 4, 8, and C. And so they all map to the same set. And we can look at our block offset. This is our block offset to tell us which word we actually wanted. So the first access to address 4, here's our first address here. This is hex 4. Is a miss, and if it's a cold cache, if it wasn't there already. But the processor then goes and pulls in to the cache address 4, but also the neighboring addresses 0, 8, and C. It pulls in that entire block. Okay. And so the memory at address 4 is what we really wanted. We're going to get that. But now, in this next access to 12, instead of being a miss, which it would have been in a cache with only a 1-word block size, now it's going to go and say, oh, hit. I already pulled that in. I thought you might need it. All right, so it pulls that in. We look at address 12 and see that the block offset is 1, 1. And so now it pulls out, using that block offset as a select line for that multiplexer, it pulls out that data that it needs, which was already, magically, well, not really magic, but because of spatial locality there. So this is a miss, and then this one's is a hit, and this next one's also a hit because of spatial locality. There it is, ready to go. Uses the block offset of hex 1, 0 to select that out of the cache. And so this loop goes executes 5 times. We have 3 accesses per loop iteration. So 5 times 3, the number of total accesses or load words is 5 times 3. 6, but it's a 5. 5 times 3 equals 15. The number of misses, well, just that first one was a miss. We have just a single miss. So the number of misses is just 1. And so our miss rate is 1 out of 15. And so you can see the advantage of spatial locality. So again, these larger block sizes reduce compulsory misses by using spatial locality. If an access to a given address is being made, likely nearby addresses will also be accessed soon. So as a review, the type of misses that we have are compulsory misses. This is the first time data is accessed. We're compelled to pull that into the cache. The second type is a capacity miss. The cache is too small to hold all the data of interest. And the third is conflict, where data that we need maps to the same location in the cache, and so they kind of knock each other out of the cache. Miss penalty is a new term, and it's the time it takes to retrieve a block from the lower level of the hierarchy. So as our block size gets larger, it's going to take typically longer to pull that into that level of the hierarchy. So here's a recap of cache organization: capacity, capital C, block size, lowercase b, number of blocks in the cache, capital B, capital C over B, number of blocks in a set, capital N, and number of sets is the number of blocks over the number of blocks in a set, or in other words, the number of ways. So this is, we also call this simply number of ways. So for a direct map cache, the number of ways is just 1. Right? We only have 1 way in that set where we can store that data. And the number of sets is capital B. B over N is just B over 1. And for an N-way set associative cache, again, simply called just an associative cache, we have at least 2 ways and less than the number of blocks. And the number of sets is then B over N. For a fully associative cache, the number of ways is equal to the number of blocks, and we have a single set. So the number of ways for a fully associative cache depends on the number of blocks in that given cache. So if it had 16 blocks, a 16-way associative cache is also called a fully associative cache. If it had 4 blocks, a 4-way associative cache in that given example would be also called a fully associative cache.